And here's the proof. Proof.
So it's the same thing, but just the proof.
So it's the proof on this statement here. Yeah. That's just in one line.
All of that is one statement.
Let S be subset of the natural number n that possesses the two properties. One belongs to S. You've written that already. And if K belongs to S, then K plus 1 belongs to S. That means that the set S is actually the same as set of natural numbers. Okay. So the proof goes, suppose, and the proof starts with, it's one of those ones, unfortunately, depends on the contradiction. So if this is the principal statement, says, let's suppose the opposite. So let's suppose this to be true. S is not equal to M. Then,
What the fuck?
yes,
Oh, okay.
yeah,
It's not a plus.
no, it's right.
Yeah.
There we go.
Okay.
Good catch. Then let's suppose that S is not equal to N. So imagine in your head you got the S. It's not the whole line like it ended up previously. Then the set N is not empty. Okay, so that's fancy stuff there. This is the set N backslash S. It says this set, all the elements in this set are the elements of N that don't belong to S. So that's what this is the all that. So this set will contain all X that are in N,
But not S.
but X's that are not in S. So only X's that are not in S will be in here, including everything in N. Okay. So what that means is that we have so let's just think again about this. So this is S. Then this part is so there's a principle called the well-ordering principle. I'm going to write it here. So in a box. I should have gone over that. I forgot about that. So well ordering, and there's a proof for this one too, but we are not going to do that. Well ordering principle.
Of course there is.
As always.
Yeah.
Or maybe it's a principle with no proof. No, I think there is a proof. I think I did do it. What this well ordering proof says that if every non-empty set, every non-empty set has, so this whole, you were saying where does the principle of induction comes from? It comes from this idea that every non-empty subset of N has a least element.
In this case, being one.
Yep. Yeah. In this case, yes. So if you have a every non-empty subset of N could be a subset that is 2, 3, 4.
Okay.
And in that case, it would be 2. But the set of natural numbers does have 1. And so it so this whole well-ordering principle states that, so that's why we end up with the base case as 1, as you just were saying. It's the logical conclusion, 1 is special. And then everything else is a K. There's only 1, 1. 1 is a very special number, so is 0. And if a set doesn't have 1, then it doesn't have
any other number.
There you go. then it is in trouble. So if that is true, then so let's suppose S is a subset of N and is not a subset of N. Sorry, S is not equal to N. These are separate sets. And now we're thinking about this set. Then the set N slash S is not empty. If it is not empty, we can apply the well ordering principle to this thing. And we can say that so by well ordering principle and slash S has a least, this thing is getting very ugly, element. And we're going to call it M as usual. And so I'm going to stick M here. And I'm going to stick M here. So here's a question here. So M of course would be right here because it's the least element. And for this subset here, N would be right here. But I just stuck it there. Okay. So just to be clear, also on the internet, that's what we've done. We should have put M here and we will move it. But right now I just stuck it there.
Well, no, M would be at the very left of S.
Right, to the right.
No.
No, there are two, and at this moment there are two sets.
Oh, okay,
Right?
okay.
There's this set and this set according to.
Okay, well then.
We started with S is not equal to. We started with.
S is not equal to the natural number.
Yeah, it did say S was a. It does, and this set according to.
Okay, well then.
We started with S is not equal to. We started with.
S is not equal to the natural number.
Yeah, it did say S was a. It doesn't say. No. Okay, so the principle of induction says that S is a subset of N.
Yeah.
That's why we have S in the middle in the red. And then we ignored this and we said, let's suppose that this condition is false.
Yeah.
We're using the conditions available here. When we did that, we got this, which meant that N slash S is not empty. If it was empty, then S and N would be the same thing. And then using the well ordering principle, if this is a subset of N, which it is, and this is a subset of N, it will have a least element M. We've chosen that letter. And it would be right here and it would be right here because the numbers increase towards the right. But we haven't put it in the right location. Now it says now we're gonna go to this hypothesis, the base case. It says since by one belongs to S, we know that M is greater than 1. Okay, so we're doing this line here, so this line here will modify our diagram. It says that 1 belongs to S, so we need to put 1 in there. So I'm going to put it in the right place, just for the hell of it. When I do this, this falls off. So the set of natural numbers is nothing to the left of the set of natural numbers. So we can get rid of this. Now it turns out there's only this part that we can even call big N slash S. Okay, so this is the smallest element of S, and then M is, so it's still not in the right place, so we're gonna move it. So so we know, right now we know that M is the least element and it should be here. We put the one in the right place in our diagram, and it says, so, but we're not gonna do that yet. It says, next thing is, but M greater than 1 implies that M minus 1 is greater than 0. So this is simply right. What we did here was add minus 1 to both sides. And then this becomes 0. And we are left with this.
Yeah.
And remember in math, what the hell is this? This is a number. If this is a number, it's saying that this number is greater than 0, it's a positive number. If it's a positive number, it's going to belong to this set here, right? So let's stick it here.
I mean, it could also be an S.
It is,
Yeah.
yeah, because M is right here. It falls in there,
Yeah,
and that's what happens. So,
that makes sense.
yeah. And I think this step here, I'm overdoing it. Okay, so I'm going to now put,
You just gotta put M in the right place.
yeah, I'm gonna put M in the right place because I've been delaying it for too long. So I think at this stage we can do that, or even before. So, and I'm not sure which is more efficient. So M is now here. Let's keep M here, and then M minus 1 falls in here. Okay. So since M minus 1 is less than, now we know. So this is a positive number. And since we know that M minus 1 is less than M, and M is the least element, and M is the least element, and this is all in the proof, in N backslash S. So therefore M has to be here. Therefore this falls in there. And we have to conclude that M minus 1, which is a positive number, belongs to S. This is our conclusion. So put it here. Therefore, M minus 1 belongs to S. So now what are we gonna do? Well, we're like,
Yeah, I don't know.
apply number 2. We did this, right? We took the opposite of this. We've already applied that. Its turn has come in because we found a K here.
Is K gonna be on the outside?
Let's see what happens. So we're gonna do this. We're gonna apply this, and our K is going to be this guy here. Small k.
M minus 1 is K?
Yeah, and minus 1 is our K. And then we're going to, because it belongs to S, it's bigger than 1. We're gonna do 1 on, we're gonna add 1 to it. So I'm gonna erase this.
I'm gonna write condition 2.
Yes. So we're applying condition 2. So we say, we now apply This is something very assuring and like, I don't know, happy about proofs.
It's just cool.
Yeah, it is. It is weird. I'm kind of addicted to this shit. Okay, and that is hypothesis 2, which means that then k equals m minus 1. And now we can say, and it is in S, right? So we can say if k equals m minus 1 belongs to S, then by the principle of induction, we're going to add 1 to both sides of this thing. Which implies that k plus 1
Equals M.
very good. And where the fuck did m belong to? On this line here, right?
Yeah.
By hypothesis 2, m actually belongs to
S.
S, not to this. But right now it is belonging to both. So this is what? A contradiction. Therefore, our assumption that S does not equal N was wrong. And in fact, S does. So we have so let's write that so that, and this will be our last sentence. We see by number 2, this is called, okay, sorry. Now I'm getting nervous again. Inductive hypothesis. I can't even say this word. Hypotheses. So we see by number 2, the condition 2, the inductive hypotheses, that M belongs to N and M belongs to S. This is a contradiction. Therefore, our assumption that S not equal to N is wrong. And is wrong, and that in fact S equals N, and that's it. Therefore, yes.
Square. Right. Square that fills in. It's over.
Oh yeah, the almost. Or you can do QED, which used to be the traditional. Nowadays it's a square that you can fill it, or actually I wouldn't fill it because that's the ink.